decided to talk about briefly about two topics where we worked on theoretical aspects, but then, I mean, there is also a direct impact on applications. And so one of them is interpretability. So there you will see how we continued what I already talked about, I mean, some time ago. And then there's another aspect on graph convolutional networks, or you got, I think, also quite maybe interesting results, which also points towards how to best use these networks. But as Michael already said, I mean, I moved, so I thought I brought you a couple of pictures from the Ludwig Maximilians University in Munich, which is the other university. The other is a technical university. So here you see the main building. That's the inside of the main building, our most beautiful, let's say, lecture hall. And so this is the city of Munich, where you see here the main building, the main campus. But I mean, LMU is a city university, so it's basically scattered over the city. And so this is the chair I'm heading now. It's on mathematical foundations of AI. Okay. Yeah, so let's start. I mean, as you know, I'm interested in driving theory further, but with an eye towards applications. And so these are, let's say, the main directions in that area which we see. I mean, there's a question how to design architectures in a particular way, how to design the learning algorithm, generalization aspects. So why does it perform that well neural networks on out of sample data, and also interpretability. You have a fixed neural network, and the question is, how does it reach decisions? And so in this talk, I would like to very briefly touch these two last points, and again, also with an eye on what, I mean, if you use neural networks, what can it tell you from that? So let me start with generalization. And so these are the people I collaborated with, a very brilliant postdoc, Ron Levy, who also now moved with me to LMU. Then two students from Italy, and yeah, Michael Bronstein from the Imperial College in London. Yeah, I think generalization is still one of the big mysteries in neural networks, because, as it says, the key observation is typically, I mean, if you look at the training performance and test performance, there's a small difference, in particular if you go to really highly parameterized neural networks. And it's not really clear why that's the case, why, in a way, the classical theory, statistical learning theory, kind of breaks and can't explain that phenomena. So there could be different reasons. The architecture could be nicely designed, maybe you regularized during training, but somehow, I mean, all of those don't really unravel the mystery why this actually happens. And I would like to now look at this question from the perspective of graph convolutional neural networks. So graph convolutional neural networks can be seen as a generalization of standard convolutional neural networks, because now you just don't have only signals on the Euclidean domain, like vectors in Rn, but you have actually signals on graphs. And you can imagine, I mean, it has numerous applications these days, recommender systems, fake news detection, also chemistry, and so on. So graph convolutional neural networks right now are used for a huge variety of different questions. And this question concerning generalization becomes there, in a sense, also even more difficult, but it has interesting, let's say, partial questions. And one question is the following. So if you train a graph convolutional network, you have to show it a lot of data on graphs, but now it could happen that it sees maybe some data on particular type of graphs, but maybe there are other data on other graphs which mimic the same phenomena. So you have maybe data on this graph and you have data on this graph. And so maybe it's just the same phenomena, which it's mimicked that way. It's only maybe different discretization of it. So maybe there's a continuous phenomena which is discretized in two different ways. So if the graph convolutional network is trained on maybe these type of graphs, it should also generalize to these type of graphs, which give you the same phenomena. You want to have the same decision in the end. Yeah, so this is in a way part of the problem of generalization. And so this is the concept of transferability. If you have two, let's say, graphs, so you have each node, you have some value on the nodes, but both come, let's say, from the same continuous function. Then if you now throw your graph convolutional network on it, I mean, then this should have the same repercussion on both graphs. Yeah? So there should be not a difference. If this is decided to be 1, then this should be also decided to be 1. And what we did, and which I will briefly touch on and then show what you can get out of it, is that this is actually true if you use spectral graph convolutional neural networks, which was before thought not possible in a sense. So this brings us to the question, I mean, how do you actually program a graph convolutional neural network? There are two different approaches. One is your filters can be designed in spatial domain. So that means you have, let's say, somehow like a window, and then you move it on your graph, and each time you compute the convolutions this way. So you compute it directly by moving on the graph. Yeah, and so you aggregate basically feature information from the neighbors to each node. So that's the spatial approach. Sorry. The other approach is the spectral approach. So there you use basically the Fourier transform, you bring it in Fourier domain, and then you use there the convolution theory. And so it was for a long time believed that, well, spatial approaches achieve this transferability property, but spectrals do not. And what we showed is that, in fact, this is not true. So spectral approaches do satisfy this transferability approach. And also one should say for spatial approaches, there is also no proof. It's just common knowledge that it is. And so what I would like to now discuss with you is, one question is how to set up the spectral approach the right way, how to design your filters, because one needs to be careful about that. But then once one does it right, one can show a theoretical result. But I think the interesting outcome then is that numerical experiments show that, in fact, the spectral approaches very much outperform the spatial approaches on this transferability test. So in that sense, I mean, the key message is, if you have the chance to use graph convolutional networks with spectral approaches, then go for that and use it over as opposed to spatial approaches. Okay, good. So let's talk a bit about the spectral filtering. What does it do? So how do you build that? I mean, there's what's called, I mean, so let's take a look here. I mean, we know from RN, we know frequencies, we know Fourier modes. You can do the same all for a graph. You can design the adjacency matrix of your graph. You can design the degree matrix of your graphs for each node, how many connections to neighboring nodes exist, and this gives you then what's called the unnormalized graph Laplacian. So it's a particular matrix, and then you can also normalize it. So in this, you can view also as an operator. So it's self-adjoint. But what's interesting is it encodes, so the eigenvalues of it you can view as frequencies, and the eigenvectors you can view as Fourier modes. So that's a replacement for the normal Fourier transform and let's say the normal frequencies and exponentials which you would use for Rn. And here you see, for instance, if you have, let's say, discretization of this dumbbell shape, then you see here the eigenvectors of this graph Laplacian, and you see here also, indeed, I mean, you see different frequencies. So here you have, let's say, a low frequency, and then you see here higher frequencies being mimicked. But again, I mean, adjusted to the geometry of the graph. Okay, so, and now how do you define, let's say, convolutions? Well, I mean, let's say I have my eigen vectors here of this graph Laplacian. So in Rn, it would be these exponentials. Then I have my filter, so some coefficients here. And so what I do is if I have, let's say, my function on the graph, I compute this sum. And so then, I mean, this is what encodes the filter. And so this I do then, I mean, each time I compute a filter in my graph convolutional neural network. Now, this is, let's say, a crude approach, maybe the easiest one can think of, but it has serious problems. I mean, first of all, to compute this eigendecomposition is very slow. And also there's no fast Fourier transform for graphs. But even worse, this decomposition is not stable. So now if you, let's say, have a graph and you perturb it a little bit, I don't know, you drop a node or something like this, your graph, you pass through your neural network, then the graph Laplacian will change. I mean, these eigenvectors could change rapidly. So in that sense, I mean, this filter would be not stable in any way. And so therefore, I mean, that way you can never get this transferability. Because then, I mean, if your graph changes a little bit and suddenly the filters do something completely different, I mean, transferability is just not possible. So you have to be a bit smarter to set up your graph convolutional network the right way. And what you use for that, you know, go too much into the details, are some things from functional analysis, which is called functional calculus. So basically the idea there is, we just explain it maybe on a high level. So the idea is, coarsely, you have some operators, something like this. And this method tells you that you can also apply a function to an operator. And so what you get then is a decomposition of this type. So basically you see, if you apply this function to this operator, it just impacts these eigenvalues. And this we will use. And so you can even write this explicitly. If, for instance, your g is a rational function, then this object you can write explicitly in this way. You see this you can compute. If this would be now your graph Laplacian, this matrix, this is a term you can compute. Okay, and so the idea now is, instead of using what we had before, we now design our filters in this way. So that means, you see, I mean, instead of choosing these filter coefficients, for each filter you choose a function. And so what your filter now does is it applies this function to this operator. So this gives you an action. But what it truly does is it computes this decomposition. So instead of having this now, you have very specific filters here. And the impact of that is the following. So this solves the instability problem, because now if you change your graph a little bit, these eigenvectors might change a lot, but the eigenvalues change with it and counterbalance the change of the eigenvectors. And you can prove that. You can show that this way you actually get stability. Yeah, so this way, this is a possibility to get, let's say, a stable graph convolutional neural network if you set it up this way, provably, and then you also have a change for transferability. And also it solves the computational problem, so you don't need to compute this eigendecomposition at all. If g is a rational function, you can write it explicitly up. So this is a particular type to set up the graph convolutional network, which is provably stable and which is also fast to compute. Okay, so now the beauty of this then is that for this you can now actually show transferability. So how do we do that in rough terms? So if we have a graph, you see, I mean, that two graphs models the same phenomena. What we assume is we have something continuous over both, and then we can go from one graph to the next. And so we have here a metric space above that, something continuous, and so we can move between the different discretizations. And then we have a theoretical result, which I don't want to explain in detail, where we have an estimate for the transferability, which depends on the transferability of the Laplacian and some additional error. But you can keep it under control. So the message here is if you set your spectral graph convolutional neural network with this particular type of computing or implementing the filters, then you know it is transferable. And you can also see that numerically. So from a numerical viewpoint, you see there are different ways what transferability means. One, you could say, is concept-based transferability. So you have a training data set which consists of multiple graphs. Multiple graphs which maybe also sometimes mimic the same phenomenon. Then if the graph convolutional network is already exposed to this during training, the hope is that it already learns the concept of transferability during the training phase. Because then it already sees there are different graphs which mimic the same phenomena, and so this should lead to the same outcome. So then there's another transferability which one might call principal transferability. So this is, you just have from one phenomena just one example. And then the question is, can the neural network transfer? And this can only happen if there's, let's say, a built-in capability of graph convolutional networks to do that. Because it has never seen that in training. It has to do that in some sense, in some inherent way. And so the reason why spectral graph convolutional networks with this particular design of filters are that successful is that they kind of rely on both types of transferability. One example one can look at is this. So you have, here the question is the following: you have an image and you have a resolution of it. And the neural network just sees one resolution. So let's say an image of a cat, you have a particular resolution. And the neural network learns that with this resolution, it says this is a cat. But now, during testing, it sees the same image with different resolutions. And certainly we hope that again, it says each time this is a cat. And what one can see is that now if one exposes this neural network to different image resolutions, and this is the accuracy, that then the KDNet, which is actually the spectral graph convolutional network, performs much better than the spatial approach. So here, I mean, this is this built-in capability of the spectral graph convolutional network for achieving transferability. So generalization ability in that sense. And then, I mean, we published this paper, and then some colleagues from Australia, I think, did an extensive empirical study on transferability. So again, what they did was they tested everything in the single graph setting and then looked at what if you now, let's say, use other graphs, what happens. And so they tested different tasks, at different rules, and the basic outcome which they then had was that indeed, so this is a particular spectral graph convolutional network which has this implementation of filters I talked about, that this indeed reaches state-of-the-art results. And often, if you actually look through all those tasks, you achieve the best accuracy, and you see it's sometimes even much better, significantly better than all other approaches. Yeah, so I mean, here the message from this part is that spectral graph convolutional networks are, I mean, it's recommendable to actually use those with this particular type of filtering, because they are, you not only have theoretical results, but also numerically it shows that they perform much better on those tasks. Okay, so that was the first part, what I wanted to show you. And the second is just a brief update on the work you're already familiar with. And so this is now, in a way, the team with which we drove this a bit further. Again, Ron, you see it involved. John Brunner, you might know from NYU, and then a student of his and a master student of TU Berlin. Okay, and maybe I don't need to go too much into the details on this. Yeah, so the question is, I have, let's say, an image, and I would like to detect which parts of the image are how important for the decision. And I think last time I also already explained to you the idea which we had there. So what you want is you have your image, you want to deem certain parts of your image relevant and the others not relevant. And so the way we went about that was we ask, if I now take out some pictures, some pixels, and I obfuscate them, do I still get the same message in a sense? So if I pass this through my neural network and this through my neural network, is the outcome approximately the same? And that would tell us that this part of the image is indeed relevant for the decision. So this is what I talked about last time. And you can set up, so this was then the error which you make. So you have your original image, you have the one where you take out a part and obfuscate it with noise, and you look at the error. And certainly what you want is you would like that the number of pixels which are relevant is sparse. So you want a sparse explanation. And then we talked about that, in this setting, just deeming that a pixel is relevant or not, the problem becomes NP hard. So you need to relax it. So instead of having a relevant set, you have a relevant score at each pixel. So you give each pixel a value between 1 and 0. And so then, you can, again, you get the error, you get, let's say, the rate, the size of the explanation in a sense, and then you can set up a minimization problem which solves your question. So you have here the error, you have here how many pixels are in your explanation, and you can imagine if your explanation is more elaborate, then the error will go down. This is the case also in human communication. If I have, 2 hours to tell you something, then you might understand it much better than if I just have 1 minute to tell you something. And so this is, in a way, this minimization problem which balances between the size of the explanation and the error which you make. And then we went from there and asked ourselves, first of all, do we really obfuscate this with random pixel? Because it creates a very artificial image. And the network, it might be very much out of the data manifold, which is reasonable. So can we obfuscate it in a more natural way? And also, these pixel-based explanations, if you now use other types of data, like audio data or something different, then, you want to go beyond that. And so what we did was so this was our original, let's say, explanation. So there you have the Y, and the Y is your image where you have a part of the original image, and then you obfuscate it with random noise. And so then this is the error which we got. But then there was other work by colleagues which, for slightly different tasks, they used an in-painting network. And so then the idea now is to take this and not obfuscate it with random noise, but to use an in-painting network to obfuscate it in a more natural way. And so this is what this leads to. So now, instead of taking here for Y, so you see here you have your original part, in some, let's say, degree, and you have the other part, but here instead of the other part, you don't use noise, but you use your in-painting network for it. And then again, solving this optimization problem, you have the error here as before, and here we have the size of the explanation. Yeah, and now, to apply it to different modalities, you can basically transfer it to that, but to make it even more flexible, what you could also do is you can apply a transform, let's say, to your image, like a wavelet transform, and then you can actually analyze the importance of each, let's say, wavelet coefficient instead of each pixel, and this gives you clusterings of pixels which are then important or not. So that way you get a very general and flexible approach. And then we, for instance, applied this to audio data. So there you can wonder if you have a musical signal, which instrument this is. And then you can ask the question, what does the neural network use for the decision? Is the magnitude more important or the phase? And certainly, I mean, we all know that usually the phase should be more important for audio data. And with this interpretability approach, we also saw that indeed the neural network looks more at the phase information than the magnitude information. And another application which comes now from a very different area, from telecommunication, you can also ask interesting questions. So what is the problem here? So this is a collaboration with a colleague from EE. You have a city map. Then these red dots, these are people with a cell phone, and they, you know, the strength of the signal they receive. And then you have here the position of the cell tower. And now you just want to compute for each point of the city how good the signal is there. So you want to compute this black and white background image. And so we use a combination of 2 units for doing that. That works quite beautifully. But then you see here, for instance, this black dot appears, which is very strange. I mean, why should the signal reception be that bad in that area? And so then you can use these interpretability approaches and ask, I mean, how did the neural network come to that decision? And what you can find as an explanation is that, well, it looked at those people and they actually had a bad reception. So therefore, it decided that something needs to be there. So there the reception needs to be bad. And in retrospect, what we then also found out was that in the city map, a building was missing there. So in that sense, I mean, the neural network did a smart decision, and you can also verify whether the neural network did something sensible. Okay, so this is the extension of this part. And so in a very brief, in a nutshell, what I wanted to discuss with you was once, let's say, this aspect of generalization of graph convolutional networks, where we found out that the spectral version is actually much better than the spatial version of graph convolutional networks if you do it in a smart way. So if you set up your filters the right way, then you can not only prove transferability, but you can also see it numerically that it performs much better. That was one part, and the other part I wanted to update you on what we did concerning interpretability, that we now think we extended it to a well, nicely general and flexible approach, which you can then also use for different modalities, and which gives, I think, very interesting explanations. Yeah, that's it. Thank you very much.